So we have already discussed how to find gravitational potential to a given mass distribution. Now I'll be talking about gravitational potential energy of a given mass distribution. The mass distribution can be of two kinds. It can be system of discrete masses, or you can have system of continuous distribution of mass. It can be system of discrete masses, or you can have system of continuous distribution of mass. So let's try to define how to find. Let's try to see how we can find gravitational potential energy for the given mass distribution. Suppose we have, say, system of n discrete particles, system of n discrete particles whose positions are described by, say, R1, R2, Ri, Rn. That is, we have, say, n particles, n discrete particles, and we want to find gravitational P of those system of n discrete particles. We have mass m1 over here, m2 over here, m3 over here, mi over here, and mn. Right? Suppose this m1 is described by r1 vector, m2 is r2 vector, m3 r3 vector, mi ri vector, and this is mn. Right? So this is r1 vector, this is r3 vector, this is rn vector, this is r2 vector, this is ri vector. So this is the mass distribution. This is the mass distribution. This is system of n discrete masses. So how to find potential energy of this system of n discrete masses? How to find potential energy of system of n discrete masses, right? How will you find this? See, before you find gravitational P for given mass distribution, or you can say given mass configuration, what is configuration? Arrangement of particle in a space. The arrangement, overall arrangement of masses or particles, that's called configuration. So you want to find gravitational P for a given mass configuration. You want to find gravitational P for the given mass configuration. So how will you find potential energy for a given mass configuration? See, before you find potential energy for the given mass configuration, first of all you think of that configuration of the given system. You are given a system of n particles and you are asked to find out potential energy for this system of n particles for given mass configuration, right? So before you find out potential energy of given system for given mass configuration, you first of all you think of that configuration of the same system for which you can assign zero potential energy. Before you find out gravitational P for given configuration, you just try to imagine for what configuration of the same system, you can assign zero potential energy. What would be the reference configuration? What would be the configuration to which I can assign zero potential energy? Right? So how will you determine that? See, before you determine for what configuration you can assign 0 P, you first must know what potential energy actually defined. Potential energy is defining, potential energy characterizes configuration basically. Potential energy characterizes configuration. It is something which characterizes configuration. So we are having a question that for what configuration the given system, for the given system of particles, I can assign 0p. So to answer, to get this answer, you must know, see, we are into classical mechanics. Mechanics is or mechanical system. In mechanical system, what do you study? You study system of particles, and this system of particle will undergo interaction. God has made all the system interactive. Almost all the system which you have is interactive, right? Do you agree or not? It is. Every system which God has created is interactive. If you are having a classroom of 50 students and I ask you that all of you shut your mouth, shut your ears, what else you can shut? Shut your eyes. You can't shut your nose. So you shut your eyes, shut your mouth and shut your ears. And I ask you that you remain as it is for 4 hours. Will it be possible for you? Will it be possible for a classroom to shut his eyes and classroom of 50 students, where every student has got shut his eyes, mouth and ears? So will it be possible to remain there for 4 hours or 3 hours, even for 15 minutes? It is not possible. Why? Because God has made us interactive. God has made us interactive. So whenever we are together, we are having good number of people around us, we always try to interact. If somebody is not interacting, that is not his behavior which he wants from core of his heart. If somebody is not interacting, that means he has made not interacting as his policy. I can't agree with the fact that somebody don't want to interact. Every person is interactive. In fact, every non-living thing which God has created is also interactive. These masses, see these masses, we have n particles. We have these n particles. They have been created by God. They are interactive. They are interacting through gravitational forces. So whenever you have system of particle, you will have interaction. And the sole objective of studying physics of any system is to study their interactions. How better you can understand the interactions? How better you can understand the interactions, right? And there are many physical quantities or many physical attributes which is emerging as a result of interaction. One such physical attribute is forces. Force comes out as a result of interaction. Force comes out as a result of interaction. If we have, say, classroom, suppose we meet for the first day. When the classroom assembles for the first day in any course, and imagine that nobody is knowing each other. Suppose we have a classroom on the very first day, we don't know each other, right? Then over a period of time, when 8 or 10 classes have gone, we have interacted over a period of time, and then some of us become good friends. Over a period of time, we undergo interaction, and some of us become good friends. So friendship is what? Attractive force. Leads to attractive force. Or some of us may not like to see each other. That is repulsive force. That is also outcome of interaction. That is also outcome of interaction. You can't see a stranger on the road and say you are a good friend of mine. Can't say this. Why? Because forces comes out as a result of interaction. Or you can't say someone that you are not good man, you are a bad man. Can't say this. You can say this only when you interact with that person over a period of time. So forces comes out as a result of interaction. And there is one more thing which is coming out as a result of interaction, that is configuration. And configuration is something which is characterized by potential energy. So the question here was, for what configuration I can say potential energy is 0. Then you get the answer from here. the configuration where the particles are not interacting, that will be a configuration for which we can assign 0p. Since configuration is the outcome of interaction, so a configuration of same system, where the particles are not interacting with each other, that will be a configuration to which you can assign 0 potential energy. Is it a nice way of doing this? Yes. So the configuration where the particles are not interacting, that will be a configuration to which I can assign 0 potential energy, right? So we got the configuration for which we can assign 0p. Now potential energy of system of particles for given configuration will be what? We have got the configuration for which we can assign 0p. That will be a configuration where particles are not interacting. And which configuration of particles are not interacting? A configuration where particles are all lying at infinite distance from each other. Because you see, gravitational force has got inverse variation with distance. So a configuration where the particles are all lying at infinite distance from each other, that will be a configuration where particles are not interacting, and that will be a configuration where for which we can assign 0p. Then once we do this, now it is very clear. Now once we got the reference configuration, then gravitational P for of a system of particles, for a given configuration is equal to work done by external agency in transforming the given system from configuration of zero p. You got the configuration of 0p to given configuration. And remember, when we do this configuration, that is, in bringing the particle, how do you transform? By bringing the particles from infinity to the existing position such that none of the particle is ever accelerated, or they always remain in the state of quasi-static equilibrium is called gravitational P. Yes, is called is not needed. We have written here. Yeah. So what I have said, gravitational P of a system of particles for a given configuration is equal to work done by external agency in transforming the given system from configuration of 0p. I told you how to find the configuration of 0p. Configuration of 0p is a configuration where particles are all lying at infinite distance to the given configuration. And how do you do this? You do that by bringing the particle from infinity to the existing position, right? The same thing, transforming the, or you write this is same thing, right? I just told you how to transform a given system from configuration of 0p to given configuration. That is do by bringing the particle from infinity to the existing position such that none of the particle is ever accelerated. Why this? It is because if you accelerate these particles, then your work done by external agency will no longer be equal to the potential energy. Then in that case it will be equal to potential energy plus kinetic energy, because a part of your work done will get converted into motion. So it will be, this equality will work only when all your work done is involved in changing configuration and none of your work done goes into creating any motion. Then only this equality will work. So this is the condition for numerical equality between work done and gravitational PE. So gravitational PE of particles for a given configuration is equal to work done by external agency in transforming the system from configuration of 0P to existing configuration such that every particle remains in the state of quasi-static equilibrium. I have already explained to you what is a quasi-static equilibrium. So this is how we define gravitational PE. This is how gravitational PE is defined. This is how gravitational PE is defined. Let me take an example to illustrate my point. Suppose we are having say 4 particles lying at the vertices of a square of say side length A. Suppose we have a square of side length A and say we have particle of mass m over here, say 2m over here, say again m over here and 3m over here, right? And I want gravitational PE. Of course this mass has to be very large, only then your gravitational PE will be considerable. So we have this system of 4 particles, say the side length is A, they are lying on the vertices of a square, and I want to find gravitational PE of this system. I want to find gravitational PE of this system. Let's label these particles, call it particle number 1, this is particle number 2, this is particle number 3, let's call particle number 4. You labeled it, okay? Now, so as per our definition, gravitational PE for the system of particles would be work done in bringing these particles from infinity to their given position such that none of the particles is ever accelerated. So suppose this is the configuration. Now initially all these particles are lying at infinity. Suppose all these particles are lying at infinity. So initially I am assuming that all these particles are lying at infinite distance. All these particles are lying at infinite distance. Now let's bring the particle one by one from infinity to their given position. So suppose we bring this particle first, or whichever particle I bring first, let's call it m. So let's bring this particle first. Whichever particle you bring first, you call it 1, right? So there is no loss of generality when I say I bring this particle of mass m first. So what is work done in bringing this particle? See, when I bring this particle, there was no other particle in the vicinity. When I bring this first particle, there was no particle in the system. All the particles were lying at infinite distance. So when I bring this particle, while bringing this particle of mass m, this particle does not experience any force, because in the system you don't have any particle. Here you don't have any particle. So when you bring this particle of mass m, it doesn't experience any gravitational force. Hence you also don't have to apply any force. External agency also do not have to apply any force, because you know Fext was what? That was the equal and opposite the force which was acting on that particle from the system, right? So work done in bringing the first particle is how much? Is 0, because this particle does not experience any force. So external agency also do not have to apply any force while bringing this particle, because the particle has to be brought in equilibrium, right? So since there was no gravitational force acting on that particle, so Fext was also 0. Okay, so work done bringing the first particle is 0. So we have brought the first particle. Now let us bring the second particle. That is second particle of mass 2m. Let us bring the second particle. So what is work done bringing the second particle? What is work done bringing second particle? See, before I answer this, let us find the answer of this question. If I bring 1 kg of mass from infinity to this position, what would be the work done? If I bring 1 kg mass from infinity to this position, what would be the work done? Work done would be simply gravitational potential of this mass m at this position. That's the definition of potential. Potential at this point is what? Potential at this point is equal to work done in bringing 1 kg mass from infinity to this position. So work done in bringing 1 kg mass is equal to potential of this particle of mass m at this point. Then what is work done in bringing 2m kg mass? What is work done in bringing 2m mass? That will be equal to 2m into potential to mass m at this position. Work done in bringing mass 2m would be equal to mass 2m into potential to mass m at this position. Because you know, work done in bringing 1 kg was equal to potential to mass m at this position. So work done in bringing 2m kg will be how much? Work done in bringing 2m mass is going to be equal to 2m into potential to mass m at this position. So that is 2m into potential due to mass 1 at this position. Is it not? So that will be the work done in bringing the second particle. Now you have particle number 1 and 2 in the system. And let's bring the third particle. Let's bring the third particle. So what is work done in bringing third particle from infinity to this position? Again we will make use of definition of potential. See, what is work done in bringing 1 kg over here from infinity to this position? That would be equal to potential to these two particles at this position. Work done in bringing third particle, say 1 kg mass from infinity to this position, would be equal to potential to these two masses at this position. So what is work done in bringing m mass m from infinity to this position? That would be equal to m into potential to body number 1 and body number 2 at this point. So potential to body number 1 and 2 at this point is going to be what? Potential to body number 1 is minus gm by root 2a, and potential to particle number 2 at this point is g2m by a, right? So we have third particle also in the system now. Now the system is this. Now I have to bring the fourth particle. So again, work done bringing fourth particle will be how much? 3m into potential to these three particles at this position. That is minus gm by a. Potential to second particle at this position is and then potential third particle at this position is, right? So this is how you can find the work done. And your potential energy is how much? Potential energy denoted by U is sum of this work done. Is sum of this work done. Okay. So this is how you can find the potential energy for a given system. Right. Okay. Now let's come to a very famous case. Till now we have not been talking about celestial bodies. We have been talking in general. So we have got the potential of two system of 4 particles, right? Before coming to Earth plus a mass system, if I given 2 particles, what will be potential energy? You have mass m1 and m2. What will be the potential energy of this system? See, in bringing m1, the work done is 0. But once you bring this m1, work done in bringing m2 is how much? That would be equal to, in bringing m1 work done is 0, but work done in bringing m2 would be how much? Potential to m1 at this position into m2, that is g m1 by r into m2, that will be minus g m1 m2 by r. So potential of this system is going to be, U is going to be minus g m1 m2 by r, right? This is a potential system of 2 masses. Now suppose one of the body is, say, earth. If suppose one of the body is earth, let's take earth as one of the body. See, if one of the body is, say, earth, like this, this center, say earth has got radius r, and I want to find what is potential energy of a person, say a mass m, standing on the surface of the earth. So applying that formula, what will be potential energy? Applying that formula, the potential energy is going to be minus GME, ME is the mass of earth, upon RE, right? This will be the potential energy. This will be the potential energy, is it not? This will be the potential energy. Okay, the potential energy of system of earth plus this person, system of earth plus this person. Get your point? This is the potential energy of system of earth plus this person, right? Now, if this person goes at a height of h from the earth, if this person goes at the height of h from the earth, right, in that case what would be potential energy? That would be, or before I discuss this case, I'll introduce to you what we call acceleration due to gravity. Then we will discuss this case, right? We'll get a formula for the potential energy when person is at a height h from the earth's surface. So what is acceleration due to gravity? Before I discuss potential energy, the famous formula potential energy mgh, I'll first tell you what is acceleration due to gravity. Acceleration due to gravity is nothing but gravitational field due to earth. That's called earth in the neighborhood. Means at the point which is not very far from the earth, that's the gravitational field due to earth. Acceleration due to gravity is gravitational field due to earth in the neighborhood of earth. So what is this G equal to? G will be minus Gm by Re square Er, or you can say the gravitational field outside earth is going to be minus Gme by R square, right? Outside, for any point outside, this is going to be the gravitational acceleration due to gravity. This is the acceleration due to gravity. At the points near the earth, this G is how much? R will be in that case Re square, and this is approximately this Er. So if I talk only about the magnitude, the magnitude is going to be, it's called G, and if I put all this value, mass of a radius and all those things, it comes out to be 9.8 meter per second square. It comes to be 9.8 meter per second square. And we have already found using Gauss law that if you have a celestial body of mass m, then this is G on the surface, and if you want G inside and outside, we already found it, I think, while discussing Gauss law of gravitation. This G is minus Gm by R square for R greater than R. That is same as gravitational field due to sphere, right? And this is equal to minus Gm, this is the formula, Gm by R cube RER for R greater than R, sorry, R less than R, sorry. That's how gravitational field is going to vary. The gravitational field is going to vary like this: G equals to minus gm by r square er, when r is greater than capital R, and equals to minus gm by r cube r er at a point inside. Okay, getting a point? This is how you can define. This is how you can define gravity, acceleration due to gravity. Acceleration due to gravity is this only. And if I want this g in terms of this g naught, what is g naught? G naught is acceleration due to gravity on the surface. See, if I want this g outside and inside in terms of g naught, how we can do this? Let's see this. What I am trying to do is, I am trying to express acceleration due to gravity outside the earth and inside the earth in terms of acceleration due to gravity on the surface. See, acceleration due to gravity on surface is minus g by r square er. So if I want the magnitude only, this is going to be gm by r square. And acceleration due to gravity at any point outside earth is, the magnitude wise I am just asking, that is gm by r square, magnitude wise. The sign only gives you idea of direction. The magnitude of vector is taken to be positive. So this is g. So if I want it in terms of g naught, this will be what? G naught r square. From here you can get this gm is what? G naught r square upon r square. So if suppose I want acceleration due to gravity, say at a height h, right, at a point this. So your small r is what? Small r was distance from center. So this is small r is re plus h, you can say, or r plus h, either rays of the earth. So this is g naught r square and r plus h whole square. So this can be written as g naught r square. And if I can take r square outside, this will be 1 plus h by r2. Or this can be written as g naught into 1 plus h by r minus 2. And then I can use binomial theorem. And this is approximately equal to g naught 1 minus 2h by r. That's g at the height h. But that will be valid only when g is very small compared to r. H is very small compared to r. This will be valid, this formula will be valid only when h is less than r of course. This is valid when this is less than 1. Alright, so this is acceleration due to gravity at height h. Now, if somebody wishes to find out acceleration due to gravity inside earth, say you want acceleration due to gravity at a point P which is lying at a depth of d from the surface. At a depth of d from the surface. In that case, see, express g in terms of this r. So acceleration due to gravity inside will be what? The acceleration due to gravity inside is going to be, let's use this pen, g at a point inside which is lying at a depth of d. The formula is gm by r cube r here, and this if I only talk about the magnitude, then g is this. So gm is what? G naught r square. This is r cube, and this r is what? R minus d. So that is g naught 1 minus d by r. That's your acceleration due to gravity inside. And here remember, see, you don't have any approximation. Here there was small approximation involved, but here we don't have any approximation as such. Right? So g naught 1 minus d by r. That's going to be our acceleration due to gravity inside. That's the acceleration due to gravity inside. Okay, g naught 1 minus d by r. Okay, Okay, fine. Now let's try to find out potential energy. See, usually you have read in your earlier classes that whenever you have a body of mass m lying at a height h from the earth's surface, then you find that gravitational P is mgh. See, this formulation has got a lot of assumption. One assumption is h has to be extremely small compared to radius of the earth, such that g can be taken as constant, that is 9.8 meter per second square. This is one assumption. Second assumption is you take potential energy on the earth to be zero, surface of earth to be zero, P is zero at the surface of the earth. That's the assumption. That's the assumption, right? That is just an assumption that you have made. So how do you get this U? See, you have made the assumption that potential is zero on the earth's surface. Then use the definition. Work done in bringing the object at this point from the configuration of 0p to existing configuration. So work done in bringing the object from h equal to 0 to this point would be how much? When you want to bring this body of mass m from here to here, what force you must apply on the body? See, when you bring this body from here to here, the body already experiences a force, which is mg. It's called weight. It's called weight. Again, the force exerted on the earth, exerted by earth on any body, can express in terms of g like this. See, force exerted by earth at any point of mass m would be what? That would be equal to gravitational field into mass of that body. Gravitational field is what? Force per unit mass. So if you have body of mass m, the force exerted by earth is going to be this, near the vicinity where this r can be taken. The distance of this mass can be taken as radius by earth, that is in the vicinity. So this is g, this is m, so it is mg. That's called weight. That's called weight. You all know this, that's why I'm not going into details of this. So my point was, where do we make use of this, under what assumption we use this? We have an assumption first that g, this h is very small compared to r, so small that g can be regarded as constant, right, at this point. That is taken as 9.8. Second assumption is P is taken to be 0 on the earth's surface. So when P is taken to be 0 on the earth's surface, then we find potential energy when the body is at height h as equal to work done in bringing the body of mass m from this point to this point, such that body is never accelerated. So when you bring the body from this point to this point, body experiences a force of mg in downward direction. Then the external force you must apply is, that should be equal to this mg. So you are applying force mg in order to lift it. See, when I discussed the definition of potential, I told you, when you define potential, you have to bring this body quasi-statically. You should not accelerate it. That's why external agency has to apply force mg, that is equal to force which earth is applying on that body. So that is force applied by external agency is mg in upward direction. So u is mg into the distance you travel distance of h. So u is mgh, positive, plus, because you are applying force in upward direction and you are displacing the body in the same direction. So work done is positive, since you are applying the force in upward direction and displacement also is in upward direction. So work done by u is mgh and bringing the body from earth's surface to this point. This is mgh. This is mgh. Okay, are you getting a point? So is there anything left? I think we have done it. Yes. I have one more point to discuss with you. If suppose this is earth and suppose if I talk in general, suppose this is point P and this is point Q. Suppose we have to take the body of mass M from point P to point Q. Then what is work done in moving the body of mass M from P to Q? What is work done in moving the body from point P to point Q? Body of mass M from point P to point Q, right? Work done by external agency, of course. See, work done by external agency will be how much? Suppose point P is, say, at R1. Of course, quasi-statically. Work done in moving the body extremely slowly from point P to point Q. Suppose body, this point P is at a distance of R1 and point Q is at a distance of R2. Okay, so see, when you do any work, you have to move the body quasi-statically. Means every time while moving the body from P to Q, whatever be the path can be anything. So whatever path you are choosing, the force, whichever path you choose, the force exerted by earth is going to be how much? Force exerted by earth on that body is going to be G. So in order to keep it in equilibrium, you must apply a force Fext such that Fext plus G should be 0. Then only body can remain in equilibrium. So Fext we are applying is minus of G. Then the work done is Fext dot dr. That's the mechanics. And Fext is what? G dot dr from R1 to R2. And this can be written as what? This can be written as, say, we'll use a very property of definite integrals. I can say this is R1 to infinity and infinity to R2, right? And this can be written as infinity to R1 G dot dr and then infinity to R2 G dot dr. Got your point? Okay. So this is minus of, or let me write like this, from infinity to R2 G dot dr and minus of minus infinity to R1 G dot dr. So this is going to be our potential at point Q and this is potential at point P. But sorry, I made a mistake in fact. See, the mistake was, we have a body of mass M, but this is not the force which earth apply on body of mass M. This is the force which earth apply on the what? On body of mass 1 kg. So force which earth will apply on the body of mass M will be mg. So Fext will be mg, sorry, make it mg, put m everywhere, right? That's the mistake. I came to know this mistake at the end. Okay, sorry. So this is what? This is m times, and what will remain? Infinity to R2 G dot dr. Just put it like this, minus infinity to R1 G dot dr. I think it is okay now. So this is nothing but m times potential at point Q minus potential at point P. Is it not? And m times potential at point Q is what? Potential energy at point Q and potential energy at point P. So work done moving the body from P to Q in a gravitational field is nothing but potential at point Q minus potential at point P. You just remember it as a formula. This will be very helpful for you. The work done in bringing the body or shifting the body from point P to point Q, WPQ, is equal to potential energy when the body is at point Q minus potential energy when the body is at point Q. So this is important. Okay, so I have discussed everything about potential energy.